Thank you very much, and thank you very much for the invitation. It's great to be here. I'm going to give you an overview of some applications on deep learning in these particular areas, which Gita already mentioned. And I thought I should start with some disclosures, which are not particularly relevant for this, but just in case if you're interested. So I'm going to show you mostly applications of deep learning, and also wanted to highlight some of the opportunities for how flexible deep learning is. And I think a lot of the advantages we have with using deep learning is that we can actually tackle a number of different challenges, going from very low level, how we reconstruct the images, how we acquire the images, to making the images look prettier in some sense, to then doing segmentation, detection, analysis of texture, radiomics type things. And then finally, of course, sort of many of what you read in the popular press will focus on what is actually having a direct impact onto patients. For example, the diagnosis or the prediction of this. But of course, actually, I think the real advantage of deep learning is it actually can transform all these different areas. There's probably also one point I wanted to make is that at this level, in some sense, there's a lot about debate on whether how much you should use deep learning for acquisition reconstruction. But I guess one fact is that in this area, everybody is accepting that you have to use computing to produce a result. No radiologist will ever look at case-based data or at sinograms data. And actually, most algorithms which are used currently are not doing simply, for example, from case-based a Fourier transform, but they're already using some reconstruction algorithm like compressed sensing or so. So actually here, I think there's a great opportunity because there's already a lot of computing and in some sense already machine learning. If you think about compressed sensing, you can actually say it is a machine learning algorithm. The next level of tasks are something where deep learning has been especially good. Doing perception tasks. I mean, everything you see in the literature will tell you that actually deep learning in many of these applications, especially outside medicine, is actually having a performance which is similar to humans or sometimes better. Of course, at this high level, I think one of the challenges is that actually when you really want to make a diagnostic decision or prediction, you need to also be able to reason about why you made that prediction and that diagnosis. And this is actually something where deep learning is not particularly good at least in the way we're currently using it. So I'm going to show you examples of all of this. And please feel free to ask questions as we go along. The first part, I'm going to start with from the bottom up of this pyramid. And the first part is hopefully something which actually I can go over fairly quickly because you've heard many of these things before. MR imaging, great imaging modality, but relatively slow, which is actually, I would argue, reasonably okay if you have static objects. But even you've seen many examples of the knee where, for example, you also still want to go faster. But it's especially problematic for objects which move. For example, the fetus inside the mother, the liver when you breathe, or the heart when it's beating. So here's an example of the data I'm going to work with in the first part of this talk. And I wanted to just highlight, when you see here this single heartbeat, this data is not acquired in a single heartbeat. So this is not the result of collecting data for one single heartbeat, but actually you're collecting data over multiple heartbeats, and you're just putting it together with an ECG triggering in the correct part, and you basically averaging over several heartbeats in an intelligent way. Now, why is it important? Because, of course, you can't stop the movement of the heart, so the heart's beating, but the patient has to hold their breath during the acquisition. And the longer you make the acquisition, the longer the breath hold becomes, and that is actually, in clinical practice, a limiting factor. Okay, so why is the image acquisition slow? Is because effectively you have to traverse k-space in a sequential manner. Of course, we can do parallel imaging, but parallel imaging doesn't mean that you traverse k-space in parallel. It actually means you're collecting multiple coils of data. Once you have collected your k-space, you can actually reconstruct the signal in a naive way, relatively simple, by just applying a Fourier transform. So the real slow part is traversing k-space, and I think you've seen many examples of this. And it gets worse if you do dynamic imaging, because you're actually collecting data over and over again. You're sampling the k-space over and over again. But for example, if you look at the heart, there's actually very little information changing at these different time points. So there is also a huge amount of spatio-temporal redundancy. And actually, in dynamic imaging, the temporal component is perhaps the most significant component where you can make efficiency savings because there's the most amount of redundancy in the temporal direction. Okay. So you have seen how you make imaging faster. It's relatively simple to do this. And the simplest idea is simply, let me just undersample my acquisition, correct? You see an example where I've undersampled my k-space by a factor of 4. I'm applying a Fourier transform to go back, and you can see that the image, of course, now has a lot of aliasing. And the aliasing is temporally changing because I'm also changing my undersampling pattern temporally. And the aim of what I'm trying to do is to effectively go back from this undersampled data, and we'll have in a moment, we can debate on whether it's better to go from this to this, or from this to this, or should we go perhaps in a sort of interleaved way of doing this. But I'm effectively trying to complete the missing information either in the image domain or in the k-space domain. And of course, mathematically, you could argue, because there's just a linear transformation between these domains, it doesn't really matter in which domain I'm going to do these operations. But I would argue it matters because you've only collected, you only know what data you have collected in the k-space domain. In the image domain, I no longer know what is a result of zero filling and what's not a result of zero, not what's a properly acquired signal. And furthermore, of course, in one domain, for example, convolutions make sense in the spatial domain. In the frequency domain, of course, a convolution has a very different interpretation, correct? So that's also something worthwhile to keep in mind. Okay. So I'm not going to advocate that you should do this, but in a naive way, you can say, okay, it's just a denoising problem. Let me take my image. It might be no longer just a scalar image. It might be, for example, a complex valued image. And let me try to denoise this image or de-alias this image by learning how this original image looks like. That's one way of doing this, but you can actually implement this in lots of different ways. And I wanted to highlight you what are the different options you have. So the first option is you're going to say, actually, I know that a transformation between k-space and image is, for example, a Fourier transform. That's my operation A here. I'm going to then convert everything to the image domain. I have everything in the image domain. I'm going to denoise it in the image domain. Okay? That's one option. Another option would be to say, actually, I'm going to use my neural network instead of the image domain. I'm using it in the k-space domain. I'm filling in the missing data in the k-space domain. Once I've estimated all the missing data in the k-space domain, I just need to apply a Fourier transform. Okay? And this is something which I think you heard Florian talk about earlier, and also something we're going to use in a moment, an approach where effectively you unroll your image reconstruction, you unroll this optimization problem, and you're going between image domain and k-space, image domain and k-space by having a data consistency term, which actually forces your reconstruction to be consistent with the data. There's also a fourth option, which simply says, and actually you might know this paper, this AutoMap paper, which simply says, forget about everything you know. I'm just going to learn everything from the k-space domain to the image domain. I don't even need to know that there is actually a Fourier transform involved. And I guess the advantage in principle of this approach is that you can, if your model has imperfections, so for example, if your image reconstruction is not simply a Fourier transform, you can actually put that imperfection into your model. But on the other hand, of course, you're losing all the advantage of, you're learning something which you know already how it looks like. So why bother learning it? Okay. So I'm going to show you one example from Joe Schlemper, who finished his PhD in our group last year and now works for Hyperfine doing these things commercially, I think, where you effectively try to do this dynamic MR reconstruction. And the way we do this is we have a network which effectively is an unrolled optimization, which you see here, these optimization blocks. And it has two types of operations. It does denoising in the image domain, so de-aliasing, trying to learn how to remove these aliasing artifacts. And then a data consistency layer where you go into k-space and you fill the missing parts of k-space, but also you retain those bits of k-space which you have measured. And actually you can weight them depending on how noisy you think your k-space measurements are. Of course, if you assume that they're completely noise-free, you might just retain the original measurements. But if you think that they're noisy, you can actually average between your estimate and your real measurements. Now, here's an example how this then looks in practice. So this is six-fold undersampling. You see that the sampling pattern changes temporally. This is the fully sampled data. And this is what you obtain from the CNN reconstruction. And you can see that actually this reconstruction really looks very close to the ground truth. You can push this even more aggressively to 11-fold undersampling. And you can see actually it still does a pretty good job. And the reason why I think this still works, and I think if you seen some of the previous talks, they typically work in an undersampling regime of 4 to 8. So this is more aggressive. But also, I think you should keep in mind that there's much more temporal redundancy in the data than there is, for example, in a 3D data set of the knee. And these models are 3D models. So they use time as a third dimension. And they can actually exploit that time dimension very efficiently. Okay? So we realized after a while that actually, of course, what you're doing is, and I think this comes back to what Florian was talking earlier about, is traditionally you have an iterative optimization algorithm which you're trying to replicate with this neural network. And actually, I should say, one of the biggest advantages of using these neural networks in clinical practice is that the reconstruction is super fast. Much faster than iterative reconstruction techniques like compressed sensing. So I can simply say I'm going to take this traditional optimization and unroll it into this long network. This has a number of problems if you do that. First of all, the longer you make that network, the more difficult it becomes to backpropagate your information through that network. But also it introduces a lot of redundancies in this. So one option is to, for example, say, actually, I want to keep that structure which I have in my traditional optimization, and I want to have a recurrent neural network which actually learns what to do at every iteration. But I want to effectively use this recurrent network to make it more efficient. So this is something which another PhD student in our group did, and the network looks a bit like follows. So we have this network, we're replacing now these bits with a recurrent neural network, and you're doing effectively we're using two types of recurrency here. One is in unfolding over the iterations of the algorithm, but the second bit of unfolding is also you can unfold over time, where time here means the time in the sequence, so the different time points of the sequence. Okay, so this is quite nice and is, I think, a quite a useful approach. The networks you get are much smaller, and you have many fewer parameters to optimize than you have in your traditional model. Okay, so actually I'm going to skip this. So this is. So here is an example of how this looks like in practice. You can see that you get with this recurrent neural networks, you get actually a better performance than with 3D networks, where 3D means here 2D plus time. The reason why I think you get a better performance, even though these networks are more expressive, is you can actually they're easier to optimize. The recurrent neural network has, I think, only a fifth of the number of parameters which you have for the other networks. So they're easier in practice to optimize. Okay. So another observation which we had is actually, if you have spatiotemporal data, is there another way you can actually exploit information about the spatial temporal domain? And this is something which was presented last year at MICI, and it uses the idea that there is in the KT domain, i.e. K-space over time, there are some correlations which you can really exploit very explicitly. And you do this by using a so-called XF transform. And let me just show you the idea of what that XF space looks like. So if you take a slice of your image, or a line of your image over time, and you visualize this, you can see that there is a lot of redundancy in the temporal dimension. And if you then apply a Fourier transform in a temporal dimension, you end up in something called the XF space. In that XF space, your aliasing pattern is going to have a very particular structure, which actually makes it easy to remove that aliasing in that structure. And there are a number of papers. If you have ever heard of an algorithm called KT-BLAST or KT-SENSE, they all try to operate in this space, exploiting that it's easier to remove aliasing in this space. And the reason why that happens is if I, for example, sample, let's assume I have only a 1D image, I have one sampling direction, so this is my K-space direction, and I'm doing a fourfold undersampling, and if I go in the time direction, I can have this sort of shifted sampling pattern in this dimension. And if I now go back into the XF space, so if I apply a Fourier transform of this data, then your sampling pattern, your point spread function is going to be spread out over space and frequency. And this actually makes it very easy to remove, because you actually get aliased copies of your object signal in different parts of your frequency. So if you try to denoise this, it turns out that this is easier to do than if you just operate on your images, on your K-space directly. So we have, let me just see. Yeah. So you can basically have a denoising network which operates in this XF space, but also an image space. So the operation you can see in this diagram here And this actually tends to work very well. If you look at what you get compared to the standard recurrent neural network, which I showed you earlier, you see you get better PSNR and SSIM measures, which everybody reports. And I think we have heard that already before, that of course that is not always the best measure to report, but it's the only one which we have in the absence of any information from a radiologist or cardiologist looking at these images. The last point I wanted to make on this is that actually in dynamic imaging you might also want to go for very, very aggressive undersampling regimes. So if you look, for example, here at a fully sampled data set, and you look at what happens when you undersample, then of course if you undersample only by a factor of 4, you can still see a copy of the image reasonably well. If you go to extremely undersampled rates, for example here, you really only have 4 lines per frame of K-space, you get very, very little spatial information about the object. Okay? But you've already seen before in Florian's talk that of course I can make a choice how wide I bin my data, my K-space data. So actually I can, for example, pool all the K-space data for the whole heart together. So I can effectively take all these different measurements I have, put them into one K-space and reconstruct an image. The problem with that would be that that image will look very blurry because the object is moving while I'm collecting the data. But what about if we can estimate the motion of the object while we acquire this? And this comes back to what Mark was actually showing you earlier. If I have a registration, if I can do motion estimation of the object, I might be able to use that during the reconstruction. So let me see, yes. So the idea in the original paper by Joe Schlemper was to create there's an image missing there. Was to generate a network which does the following. So it takes your image space, it does a de-aliasing so you get a better image. I don't really know why this is suddenly disappearing. This is not a neural network doing this. You have a data consistency, you go back, and then you get your final reconstruction. So what I'm going to try to show you here, if these movies play, is an approach where you estimate the motion in between, and you use this to augment your reconstruction. So let's assume I take 2 frames, and I try to have a neural network, for example, similar. It doesn't have to do actually a stationary velocity field. We're just looking from one frame to the next one. It's very small deformation. We just directly estimate displacements using a neural network. I can take that information I have from my 2 undersampled images, I can add some data consistency, and then I can propagate that information from one time point to the next time point and augment my estimate of the image with that. So if you see this in this movie, you see as we go through the sequence, you actually get a better and better image because I'm estimating the motion of the object and I'm filling up the K-space in a consistent way using this motion estimation. Okay? Now the one thing which is also very nice is if you train a neural network, I can actually train that neural network on fully sampled data or on undersampled data. If I train it on undersampled data, I can make sure that actually the network is invariant or not sensitive to these aliasing patterns which come. Because I, of course, can retrospectively undersample my data. So I can actually artificially generate this undersampled data. Okay? Okay. And then, so what we're going to do is we're basically adding this estimation of this data consistent augmented image in this. And again, there's a movie here missing. And that actually helps us with generating a better reconstruction very very high undersampling rates. So here is how this looks like. In the first iteration, I don't know why these movies look a bit weird. In the first iteration, you get a fairly decent reconstruction with a reasonably good motion estimation. In the second iteration, when you go through that, you get a better reconstruction with a better motion estimation, and so on. And if you then actually try to use this for entirely reconstruction, you can get a reasonable good reconstruction for acceleration rate of 16. But more interesting, you can get even for an extremely high undersampling rate of 51. So that means you only have 4 lines of k-space for every frame. You can get a reasonably good measurement. Okay? And that's, for example, quite interesting if you want to very quickly track an object and see how an object is moving, for example, for an image-guided intervention. Or this might also be applicable if you, for example, want to model contrast changes, for example, due to contrast agents as well. Good. So I'm going to stop in a moment with the reconstruction part. I just wanted to highlight one thing which, again, links to what Florian was talking yesterday about, the fast MRI challenge, which colleagues in our group also took part in. And one of the observations was that actually there are lots of different network architectures, lots of different ways how you formulate the problem. And you've seen some of them in this talk as well as in the previous talks. For example, how do you implement your data consistency? If you use parallel imaging, how do you estimate call sensitivities? How you combine all of this? What is your loss function you're using? Do you use L1, structured similarity, GAN loss? Turned out in this approach, the best in this challenge, the best approach is what typically we do when we do challenge competitions. You take a whole bunch of different networks and then you ensemble them into one ensemble estimator to get a more better estimate. And this network, I don't know whether Kirsten, whether you came up with the name or somebody else. It's called SigmaNet, and it's an ensemble network of all the different combinations of people, of things which people have done in our group, and actually worked pretty well. Yeah. For example, just to highlight that, here's an example. For example, whether you want to estimate, whether you want to explicitly use coil information from in the parallel imaging framework, or whether you want to learn this information, depending on what you want to do, you come up with different network architectures, and it's not that obvious, at least to me at the moment. You can ask Kerstin later if she has a better insight in how do you actually decide what the optimal way of combining these approaches is. And as Florian pointed out yesterday, is there are a lot of different, you can produce a lot of different reconstructions. Some of them are very good in terms of your SSIM or L1 loss function, but they can generate very different appearances. And even the ground truth reconstructions, depending on how you actually do the ground truth reconstruction, can be very, very different. And here's another example of this. I think there is some highlighted. For example, if you use these different reconstructions, you can really change quite substantially the behavior of your reconstruction. You might, for example, have a structure like this visible in one of the reconstructions, but not in the other reconstruction. And you can easily generate these very different reconstructions. So I think the jury is still out. What is the best approach to choose? But there are many different approaches, and I think you have seen a lot of them during the whole week here. And I think one of the exciting things is that these deep neural networks give you a lot of flexibility how you actually formulate the reconstruction problem and how you might, for example, combine it with motion estimation and other things. Good. So I wanted to now change slightly the application and show you some of this also applied to super resolution. And that's really clinically quite useful because when you acquire these cardiac MR images, you typically acquire one slice, another slice, a third slice. So this is not a volumetric acquisition. You do one breath hold, a second breath hold, a third breath hold. You get these different slices. But if you stack them together into a volume, you actually realize that in this volume you don't have isotropic resolution because you acquire typically these slices with a fairly high slice thickness to get enough signal into it and to avoid flow artifacts. And that's not actually very good for post-processing. So an obvious question could be to say, actually, instead of just filling out missing K-space, can I just actually learn a network which will upsample my images? And of course, in principle, you can do that. So in principle, you can just take a neural network, take a low-resolution image in, and try to upscale that image. And it will work. It will work reasonably well. But in cardiac imaging, you have, for example, a bit more information which allows you to do more genuine super resolution. So one of the things you typically have is, in addition to your stack of short axis slices, you typically acquire long axis slices in a different orientation. And these long axis slices, for example, go in this along the long axis of the heart. They have very high resolution in that acquisition plane, but also fairly high slice thickness. But at least you now have complementary information. You not only have that stack of short axis images, but also the long axis images, and you have all of that over time. So now you can actually generate a more, still probably not really true super resolution, because you really have only at most 2 measurements in your data set. But you can generate, for example, a Siamese network which actually will use information from the long axis slice as well as from the short axis slice to actually try to reconstruct a high resolution image. How do you actually get your training data for that? Well, in order to train such a network, you would need to say, actually, I need to start off with high resolution 3D data. We're quite lucky that we had over 1,000 of these high resolution 3D data sets. And actually, they are quite difficult to acquire because you need to hold your breath for around 40 seconds to acquire the images. So it's actually not that easy to hold your breath for 40 seconds. Once you have that data, I can actually simulate my low resolution data relatively straightforward, because actually the forward model is pretty well understood. I know my point spread function roughly in my MR scanner, my slice selection, my slice selection profile. I can even model patient motion, and then I can simply generate these downsampled images from my high resolution data. And then, of course, the super resolution model is trying to go the inverse direction. Okay? But the forward model is relatively simple. And here are some examples of that, where you see the short axis stack on the left-hand side. This is what you would get with linear interpolation. And I'm sure if you would use a B-spline interpolation, it would work much better. And so that would actually, should have probably compared it to a spline-based interpolation. But the CNN also does a pretty good job. And here you see the high resolution 3D acquisition. Okay? But I will also show you in a moment a case where this completely breaks down. I'll come to that in a moment. Okay. So segmentation, I mean, I guess going to the next higher level in the pyramid, that's very easy because you know how we do that. We have lots of different architectures for our backbone network. We can use a UNet, an FCN. We can use DeepMedic, and here are some examples of this. You can do many different scenarios. So in some sense, one of the really nice things about using deep learning for segmentation is that actually once you have enough training data, you can actually solve the problem. And you don't have to customize your algorithm from scratch. So we're quite lucky that for cardiac segmentation, we had a huge data set which was manually annotated, which comes from this study from Stephen Peterson's group in London. And they had annotated almost 5,000 subjects, and in total 93,000 2D images annotated. And I'm not going to bore you with too much with the details of this, but these networks, when you throw that much data at them, they just work. I don't think there's really much else you need to do. They really work extremely well. And if you look, for example, at the difference between measurements between an automated method and a consensus estimate of different manual observers, and if you compare that to the difference between two different manual observers, you realize that actually the automated algorithm doesn't outperform the human, but the automated algorithm is well within the range of the variability between different expert observers. So we're not doing better than any individual, but we're doing definitely exactly the same as just adding another observer would do. Okay. Now coming back to the point is, well, if you have so much information across in terms of segmentation, can you also then help estimate the motion of the heart better? And again, this is something which Mark explained earlier, is that obviously this is a registration problem, correct? Motion estimation is nothing else than doing registration across time. That, of course, having a segmentation will help you get a better estimate. So we thought about this. Can we combine these things? Because there's clearly complementary information if I want to segment the images or if I want to estimate the motion. And the problem which we had is we didn't have, for example, all the time frames annotated by the manual observers, but just systolic and end-systolic. And then, of course, we have to use something which is unsupervised from the sort of motion perspective, because we don't have ground truth motion fields. So we came up with a network architecture which we call MotionSegNet. I'll show you that in a bit more detail in a moment. But you can sort of think about this. The motion estimation is in some sense self-supervised or unsupervised. I don't really like the term unsupervised because you still have a loss function which computes L2 distances or whatever. And weakly supervised segmentation, weakly supervised because we don't have a segmentation for every frame. Okay, and the architecture which we have, the first part is essentially a motion estimation branch, which looks very similar to the architectures you've seen in the first talk. You have a loss function which is based on the image similarity. Can be cross-correlation or sums of squared differences. So this is your image similarity loss. And then you add a segmentation branch to this, but you're sharing your weights in the feature encoder across motion estimation and segmentation. And you can then also take the segmentation, so the motion field, and warp your segmentation to your next time frame. And that helps you with defining for those frames for which you have labeled data a segmentation loss, but also you can use this to to define a loss for the unlabeled data, because of course this is a temporal sequence where at some point you will have a labeled frame again. So what you end up with is effectively a combination of three different loss functions: a motion estimation loss, where we use here the sums of squared differences of the intensities, a smoothing term in space and a smoothing term in time for the deformation or for the motion, a segmentation loss on the labeled data, and also the warped segmentation loss on the unlabeled data. Okay. So now we can estimate, we can segment all these different structures in the heart. We can estimate motion, measure strain. In theory, we should actually be finished with everything which we need to do. But there's one problem I wanted to highlight at the end, and that is, well, actually, quite often what happens is your data, when you acquire it, is actually not as perfect as you think. For example, what often happens, you acquire your data, the patient holds their breath in a different position, and that means that your data is actually sampled like this, but you think it's actually regularly sampled. That means you get, when you put your stack of slices together, it looks like this. If you look closely, there are inconsistencies in the data, right? And these inconsistencies in the data, they have a fatal effect on what you do afterwards. For example, if you apply super resolution to this, you get this. If you apply segmentation to this, you get this. Now, obviously, you know that this patient is long dead because they have a hole in their heart here, and obviously you see the same in the segmentation, correct? Because actually, the network has not really seen these type of examples. They're inconsistent, and it actually does the best job it can in terms of segmentation or super resolution, but clearly doesn't know what's plausible or not plausible. What we really want to do is produce something like this, which is much more plausible. Okay. And you can do that by throwing away perhaps your standard loss function and trying to do something slightly different during training. I'm going to show you something which we call an anatomically constrained CNN. You can use it for super resolution or for high resolution segmentation. And I'll show you in a moment how we do this. It actually has two components. It requires that you train it with labeled data. One component is nothing else than something which looks like an autoencoder. So you put your label map, your segmentations in, for example, from 3D data. You have a latent representation. You produce that same label map as output. And at the same time, you have this sort of inverted T branch of this network, which tries to predict this latent code, but not from the label map, but from directly the intensity images. Okay? So I basically have now two ways how I can predict age. One is from, if you give me a segmentation, I can predict age. Or if you give me an intensity image, I can predict age. Okay? Why is that useful? Well, because I can now train my network in a slightly different way. Let's say I want to do, for example, segmentation. The standard way you train your network is you take your low resolution input, segment it, then you get your segmentation out at whatever resolution you want. You compare it to the ground truth with a cross entropy loss. Okay? But what we're going to do in addition to that, we're using that cross entropy loss, but we're taking that shape, we're encoding it into its latent representation. We can also do that for the ground truth, and we minimize also the difference in the representation of this. So this forces the network to produce a segmentation which is not only similar at the pixel-wise level, but also similar in this latent representation code, which actually you hope would capture some information about the 3D shape, for example, of the object. And the nice thing about this is it does work, but that's one thing you can see here. But you can do the same with a super resolution, correct? Because I now have also a branch where I can predict that latent code directly from the image intensity. So if I want to do super resolution, take that image in, produce my super resolved image. Normally, I would compare it to my ground truth using the L1 norm or whatever norm you want to do. But now I can also take this image, predict the latent code from it, as well as for the ground truth, and make sure that they're also similar. Okay? So I'm using, in this super resolution, information from the shape, about the shape of the heart when I do this super resolution, because this is not only driven by pixel-wise error loss, but also by this loss in the latent code. And you can see that actually this does work. So if you do low-resolution images with some motion artifacts, if you have a baseline super resolution approach, what I showed you earlier, you'll get, I mean, it will look inconsistent because you have these errors. The anatomically constrained super resolution model gives you a much more plausible and much more similar example to the 3D high resolution ground truth. Good, I'm going to skip a few slides and go to the end. To just highlight one final sort of application, which in a minute, I'll be very quick. And that is sort of what we might want to do in the future. So if you look at sort of the traditional way how we do imaging, we do an entirely sequential process. Somebody acquires data, gives it to the next person doing reconstruction, gives it to the next person doing analysis, gives to the next person doing interpretation. So this is an entirely serial process. There is, once you've made a mistake, if you have not acquired the right data, you're screwed. You can't really do anything about that. If you've made a mistake in the reconstruction, you might not be able to analyze the data. And obviously, if you made an error in the analysis, you cannot interpret the data. But because it's serial, there is no way for it to recover. A much better way would be to say, actually, why don't we couple these different processes and perhaps optimize them jointly in an end-to-end fashion, correct? Because at the end of the day, I really care about the interpretation. Actually, this image reconstruction is purely a mechanism of getting to the diagnosis, correct? I don't really, of course I can define a loss function here, but actually in a real setting, I'm not really interested in minimizing that loss function. I'm interested in minimizing this loss function here at the end. So if we could do that, actually we could have much better optimization, much better coupling of this, and optimize the entire imaging pipeline. Hopefully that would add some value. But it also raises the question, do you actually, in this scenario, still need images at all? Why would I care about reconstructing images, segmenting images, if I do that? And perhaps that's an interesting way of thinking about this. I want to just show you one example, which is some work which we published a year ago, so that you might be able to do this. And this uses these TL networks, which I showed you for super resolution and segmentation. Instead of trying to segment the heart in a fully sampled image, why don't I segment it in undersampled K-space data, which looks like this, 20 lines of K-space, and I don't care about image reconstruction here. 10 lines of K-space, and you wouldn't believe this, 1 line of K-space. You're also starting to see that you're getting errors. You're not tracking here the heart very closely anymore. But it always produces a shape like a heart because I've actually encoded that as prior information, correct? So I'm estimating from the diaphragm. I now have a network which estimates from K-space the latent representation directly. It doesn't go via the image. And this might be something interesting to take forward in the future. So with that, I just wanted to stop here and acknowledge all the students, postdocs, and colleagues in the group, and also all our clinical collaborators. Thank you very much.